Welcome back to our sequence on the engineering design cycle. In this session, we will introduce basic principles in testing and evaluating an engineering design. Depending on which iteration of the design cycle the design team finds itself in, testing and evaluation may involve basic demonstration of functionality, or it may involve more extensive characterization and multiple data sets of valid experimental results. Regardless, all testing and evaluation should relate back to the engineering design in a way that allows the testing to cover the full scope of the design and the corresponding design specification. In the process of testing and evaluating a prototype, the design team will almost certainly be tasked with backtracking in the engineering design cycle. The likelihood of a trouble-free testing and evaluation phase is small, for sure. Testing and evaluation should begin at the component phase. All components should be verified to be functional and working before moving on to subsystem and then finally systems level testing of an engineering design. In this session, we will take a look conceptually at what component testing will look like, and then do a more detailed look at an example of component testing in an engineering design. Many engineering designs, if not most, consist of multiple components that require varying degrees of testing. For example, a custom designed sensor in an environmental monitoring system will require more extensive testing than an off-the-shelf microcontroller. This neither means that all possible experimental conditions should be presented to the custom sensor, nor that the microcontroller should be assumed to be operational and not be tested at all. Rather, it only means that both components should be tested prior to being combined with any other components, and also that the off-the-shelf or more reliable components should be tested less rigorously than the unknown, new, or custom component. Component testing is then followed by subsystem or full system testing. System testing should never proceed without both testing and documenting the proper operation of components first. As an example, let's look at a system designed to monitor wrist posture for risk of carpal tunnel syndrome or related health problems. This system consists of the main component of two magnetometer magnet pairs placed on each of the user's wrists and hands, and supporting components including a microcontroller and Bluetooth or wireless interface. As main or custom components, the magnetometers and magnets linked to the operation of these magnetometers will be tested more extensively than the microcontroller and Bluetooth interface because they are custom designed for this system, this application, and this engineering design. In this example, our primary component, a magnetometer and magnet mounted on the wrist and hand of the user, are sensors and will be tested in a hierarchical or increasingly complicated way to arrive at the sensor's successful functionality in the context of the wrist monitoring system. Comprehensive testing of the main sensor component can proceed roughly in 4 phases, from a well-controlled and isolated situation to a testing environment which represents the extremes over which the sensor is expected to operate in its end application. Testing of this component should start by isolating the component as well as by controlling the input to the component. In the case of a magnetometer, we can isolate the component by placing it in an environment that is free from stray magnetic fields. We can control the testing situation by placing the magnet at known and measurable angles to and distance away from the magnetometer. Under these conditions, both controlled and isolated, we expect that the sensor output should be normal, and after using appropriate tests to confirm a Gaussian distribution of the data, we can then determine that the accuracy and precision we calculate of this sensor are a function of the sensor alone, and not the environment or other influences external to the sensor. As we move into phase 2 of testing and allow the magnetometer to be in an environment typical of the application, where stray magnetic fields may be present, we can still control the angle and distance between the magnet and the magnetometer. A lack of Gaussian behavior under these conditions can represent a destabilizing influence or interferent in the environment that must be addressed for the design to be successful. If the data, however, are normal under constant input conditions, any resulting decrease in accuracy and precision compared to the previous, or phase 1 of testing, can be attributed to the effect of the environment on sensor performance rather than the sensor itself. As phase 1 and phase 2 testing come to a close for our main component, it's time to evaluate the results. Are the experimental results normally distributed when the input conditions are held constant? Does the component, in this case a magnetic sensor, behave close to what is expected from the underlying theory governing its operation? And if not, can the differences be readily explained and the design adjusted to accommodate these differences? Only after these basic component issues are resolved should the design team move on to testing the component within the application environment. At this point, when the sensor or other main component is fully verified and behavior quantified in first an isolated and controlled environment, and then in a controlled environment, it is ready to move on to testing in the application environment. Often this level of testing of a critical main component is first done in typical or representative conditions. In the wrist posture example, this may mean testing the system in a typical office with representative temperature, humidity, etc. But as importantly, under typical stray magnetic field conditions from such sources as office equipment, wireless routers, and other potential sources of interference. If a component performs well under these typical conditions, it can then be tested under most suspicious extremes, or those limits of operating conditions that are most likely to lead to design failure. For example, in this system, does the wrist posture sensor need to be tested next to an MRI machine to evaluate whether it can still function properly in the presence of extreme environmental magnetic fields? It's up to the design team to determine which operating extremes most need to be tested, as it is unlikely the team will have the resources or the time to test all possible extremes of component operation. Testing main or custom components, in this example a magnetic sensor operating within the application of monitoring wrist posture, can be quite extensive and take up a significant period of time. Some of that time is consumed simply in collecting data, but some will almost certainly be lost in having to backtrack in the engineering design cycle to fix any failures to meet the design specification that arise. Once the main components are tested, however, the lesser or secondary components are much quicker to test. Basic functionality of the Bluetooth modem, for example, will simply mean verifying that the Bluetooth can successfully transfer the analog signal from the magnetometer to the signal processing phase of the system. Similarly, testing the microcontroller can involve quick, isolated tests to ensure that it is performing the functions needed, such as certain computations, memory storage, and memory access, that will be required of the component in the application of the design. We can certainly be optimistic in assuming these secondary or off-the-shelf components will work properly, but not so optimistic that we ignore testing them altogether. Instead, we should seek simple tests that verify that our off-the-shelf secondary components simply work as advertised. While it can be very tempting to skip over component testing or race through it to get to the system testing, proceeding through a more logical and rigorous testing protocol for both primary and secondary components of an engineering design is well worth the effort to identify potential problems and pitfalls in the overall design. In this session, we've looked at an example of a sensor system that has gone through multiple phases and levels of component testing. Different systems will require different forms of tests and different means to isolate and control testing conditions, but they will all require that before the system is tested, the components are tested first. This concludes our session on basic testing and evaluation of system components. Thank you for joining us. We certainly hope that this session has aided you in understanding how to begin testing and evaluation of a design prototype, and that you'll join us again as we take a detailed look at other phases of the engineering design cycle.